Hello and welcome once again for another ES 340 example problem. So this will be example problem 2 for day 6. And what we have here is a tank open to the atmosphere. Initially contains 2 pounds, that should have been pounds, sorry. 2 pounds. Oops. Not doing so hot right here. 2 pounds of liquid water at 80 degrees Fahrenheit and 0.4 pounds of ice at 32 degrees Fahrenheit. So it has a mixture of 2 different substances here. All of the ice melts as the tank contents attain equilibrium if no significant heat transfer occurs between the tank contents and its surroundings. So now notice we're taking the system to be the ice plus the water, the 80 degree Fahrenheit water. That whole thing is the system. And so there's no heat exchange between the system and its environment is what we're assuming here. Determine the final equilibrium temperature in degrees Fahrenheit. For water, the specific enthalpy change from solid to liquid, specific enthalpy. This is a good problem because it brings in a whole bunch of stuff that we just learned about. Change from solid to liquid at 32 degrees Fahrenheit and 1 atmosphere is 144 BTUs per pound. Okay, so we know that at 32, 1 atmosphere, that delta H from solid to liquid is equal to 144 BTUs per pound. That is H solid minus H liquid is equal to 144 BTUs per pound. That's what this is saying right here. Okay. So we have to figure out how we get to delta H here first. So let's go immediately start with the energy balance. And many problems we're going to be doing this. We're really going to jump right to the energy balance first, and then we'll work our way backwards to find the quantities that we're interested in. So we know that delta KE for the whole system plus delta PE plus delta U is equal to Q minus W. In this case, we have a solid and a liquid. They're not going through any appreciable change in speed, right, or change in height or anything like that. The system's not really changing either of those, so we can ignore those. And we also know that there's no exchange with the environment, so this means that delta U is equal to minus W. Or, if we want, delta U plus W is equal to 0. Now, during the process when it's changing from liquid to ice, we know that the pressure remains constant. So we know that we have a constant pressure. In fact, from the atmosphere, right? on the system, because this is not a huge system that takes up a lot of height or something where the pressure is changing or over a distance or something like that. So that means that the work must be equal to the pressure times the change in volume. Remember, when pressure is constant, this is the case, right? We do the integral, you can pull the constant p out, and that's what you come up with for the integral. So this means that delta u plus p delta v is equal to 0. Now this is probably the hard part to wrap your mind around, but remember that h is equal to u plus p times v, right? That means that when the pressure is constant, delta H is equal to delta U plus P delta V, right? If the pressure is not constant, we can't do that, but in this case, the pressure is probably staying constant, or the pressure is staying constant, right? Using the assumptions that we're making, it's only experiencing pressure from the atmosphere. So this is what we end up with. And so if delta U plus P delta V is equal to 0, and delta H is equal to this, that means that delta H must be equal to 0. Okay? Now, we have phase changes going on, so that means that we're changing the enthalpy. We're changing the enthalpy by changing the volume, right? When you change from liquid to from solid to liquid, you change the volume, so you get an enthalpy change there. And then we also are going to again change the volume as we heat up the liquid. It's not going to be a huge change, right? Because we can make certain assumptions there, but there is a slight change at least in that case. And additionally, we also have to note that the water itself is also having some kind of change. So delta H has to be equal to delta H for ice to liquid, 32 degrees Fahrenheit, plus delta H for the liquid from 32 to whatever the temperature is, final temperature, right? Plus delta H for the water, because the water is cooling down. The ice was heating up, the water is cooling down from 80 to final temp. So that's what that's going to be equal to. So this means that, let's call this delta HIL. Let's call this delta H32F. And let's call this delta H80F, just for notational purposes. So delta H equal to 0 implies that delta HIL plus delta H32F plus delta H80F is equal to 0. Okay, very good. Now, what do we know? Well, we know that the change here, delta H, this part, delta HIL, was given to us in a way because it gives us the specific enthalpy change. This is what I was calling IL. That's going to be my notation here. Is equal to 144 BTUs per pound. That's the lowercase one. We want uppercase. So delta HIL must be equal to delta lowercase HIL times the mass, in this case, of the solid, of the ice, which was given to us as 0.4 pounds. So this is equal to, what was delta HIL? Well, 144 BTU per pound. And then we have 0.4 pounds, which obviously are going to cancel, and we'll just get it in terms of BTUs. Okay, then delta H 332 Fahrenheit. Okay, so this is the part that's the tricky part, and it requires us to think about some of the things that we learn. So we know that when it's a liquid, we can use the fact that it is quote unquote incompressible, right? And for incompressible liquids, recall incompressible implies that C is constant, right? The CV equal to CP equal to some constant C, right? That was the idea, the specific heat. Okay, so this is important. So we can assume that it's constant, and furthermore, we know that C at 540 degrees Fahrenheit, or 80 degrees Celsius, 80 degrees Fahrenheit, 540 degrees Rankine, or 80 degrees Fahrenheit, which is what we have here. So basically, if you take and you add 460 to the Fahrenheit, that's what we're gonna, there's actually a fraction of a unit there, but we just basically ignore that part. And this is what we get as approximately 540 degrees R. We know that C is equal to, from table, again, we have to go to the tables now, A19E that C is equal to 0.998, or approximately 1, right? It's approximately 1, and let's look at what the units are. BTU per pound degree Rankine. Okay, so because it's constant, that means that no matter what, at 32 and also at 80 degrees, right, Fahrenheit, it has to be the same value. So we have to take it to be the same value because it's a constant, and approximately that's equal to 1 BTU per pound. We're just going to round here for our purposes. It'll get us close enough, and we'll have no worries there. So anyways, what that means is delta H, recall for incompressible, for incompressible systems, it's going to be equal to, sorry, this is the 32 degrees Fahrenheit. It's going to be equal to the 0.4 pounds times the 1 BTU, that's what we just found here, the constant there, per pound degree R, times the final temperature, T final, which we don't know yet, well, that's what we're looking for, minus 492 degrees Rankine. Again, we just did the plus 460 there. Okay, and then the other thing, so basically it's C times delta T, right? We when it's at a constant pressure, recall that delta H is just going to be equal to C times delta T for incompressible substances, right? Because it was delta H was equal to, or H was equal to, yeah, delta H was equal to C times delta T plus V times delta P, right? But if delta P, because delta P is equal to 0, right? So that term just drops out for the incompressible case at constant pressure. Okay, and we know that that's true here because it's at constant pressure here, because again, we're only experiencing the pressure from the atmosphere. So that means also it's going to be very similar, delta H for 80 F, that's going to be very similar, except for now this is 2 pounds water, which we had from up here, 2 pounds, times, again, the 1 BTU, because it was constant per pound degrees Rankine, times the T final minus 540 degrees Rankine. So now if we put this whole thing together, we get 0.4, this is just this whole thing right here. We're going to put the whole thing together. We get 0.4 pounds times 144 BTU per pound plus 0.4 pounds times 1 BTU per pound degree Rankine times T final minus 492 degrees Rankine plus 2 pounds times 1 BTU per pound degree Rankine times T final minus 540 degrees Rankine is equal to 0. Now, if you add all of those terms together, what you end up finding, and I'll let you do that because it's simple algebra, but you end up finding that T final is equal to 508, approximately 508 degrees Rankine, which is equal to 48 degrees Fahrenheit. Okay, so that's our temperature. So the hard part here is not the math. It's simple algebra, simple arithmetic, but the hard part is pulling together all of the pieces, right? Remembering that C is constant in incompressible fluids, right? So that we can just take whatever C is, and we can apply it both at 32 degrees and at 80 degrees Fahrenheit, because it has to be constant. And also this part right here, realizing that at constant pressure, the delta H has to be equal to C times delta T, because delta P was equal to 0, so that final term drops off in our incompressible case. Okay, so that's really the hard part, is pulling all of these together. So I want you to start thinking about not just writing down what I say, but actually thinking about what it means, how I can use that in these different problems. And the final thing, of course, is remembering to use the energy balance equation. Hope that helps. See you again soon.